Yes, so yeah, good morning, everyone. Thank you so much for joining us today. We have the last speaker of the year, who is Adam Masters, and he will give us a really nice, I really hope, a really nice seminar about the solar wind interaction with the giant planets. And for those of you that don't know him, I'm pretty sure everyone knows him, but if you don't know him, so he works at Imperial College in London, and he works not only with giant planets, but also with Mercury, and is involved in other, in many missions. So just a reminder, like if you want, you can connect the live transcript, which is at the bottom of the screen, if you want to just see the captions. And also, like, please write your questions in the chat, and we will have a Q&A at the end of the seminar. So, Adam, if you are ready, when you want to start.
Thank you, Beatrice, and thank you for putting the pressure on. I hope it's useful, this seminar, and it's of interest to people. So thanks to all of Miss Council for inviting me to give this seminar today, and thanks to all of you for dialing in this new remote world, I guess. So I'm going to talk about the solar wind and how it interacts with all the magnetized planets in the solar system, or the strongly magnetized ones. So this is based on a paper published a few years ago. You can see the reference there. So this seminar might be a little bit unlike other MISS seminars that you've had. I don't intend to show any data, no fancy numerical modeling. It's going to be theory, but I don't want that to scare people off. It's very basic stuff people will have seen before, right the way back when people took their first courses in space physics. I think it's worth, I decided to present this because I know that there are people joining the community every year new to the field. So this is a good way, I hope, to introduce you to magnetospheric physics and the diversity of magnetospheric systems in the solar system, and to try to build up a sort of high level message about the big picture of how the solar wind interacts and drives energy through space around magnetized planets. So I apologize in advance for the equations. I know I'm breaking that golden rule. It's stated in different ways, but I hope I don't lose too much of the audience as I show more and more equations. So you can see on this title slide that the planets that are going to be most relevant for this are creeping in: Jupiter at the top, Saturn getting in on the act on the top right, and then the two ice giants, Uranus and Neptune, on the bottom right. Okay. Good. So as I said, I'm aware there are people starting their PhDs joining the field, and I think that even the new entrants to the field will be familiar with what a magnetosphere is, but I do want to go over it just so we're all on the same page and build up from the ground up. So what is a planetary magnetosphere? So it's the cavity around a magnetized planet. In the solar system, we think of the solar wind impacting a magnetized planet like the Earth, a strongly magnetized planet, and the magnetosphere is the cavity in space around the magnetized planet from which the solar wind is, to 0th order, first approximation, I guess, excluded. So in this diagram, you've got the Earth, you can see in the middle, and you've got the solar wind coming in from the left, so the solar wind is off to the left. Now, this environment that has got all this pretty color on it is completely invisible to the naked eye. It's a very low density plasma, magnetized space plasma environment. So there's a lot of energy if you consider the whole system and big scales, but it's very hard to image. It is possible, but it's difficult to image these systems. And with the naked eye, you wouldn't see anything if you were out on a spacecraft. So there's false color applied to these regions that you will see if you measure the in situ environment out there with spacecraft. So the solar wind, as I'm sure you all know, continuous, very high speed, hundreds of kilometers per second flow of charged particles from the sun, mostly protons and electrons, comes in at very great speeds, greater than the typical speeds at which you can transfer information through the medium. And so when it encounters a planet like the Earth with a strong magnetic field, because of Alfvén's frozen-in approximation, which makes it difficult for these different magnetized plasma regimes to mix, because of that, it's difficult for the solar wind to penetrate through the planet's field. So it sees an obstacle. And when you have an obstacle to a supersonic flow, you end up with a shock wave. And that's what's shown on the left here, often called a bow shock in front of a planet. So the solar wind is decelerated, it's compressed, and it's heated as it goes through that shock wave, and then it flows around the Earth's magnetic obstacle, and that region is called the magnetosheath. So that's the solar wind, but it's been processed by the shock. So it's slower and it's able to flow around, and it accelerates around the sides. And then, of course, within the magnetosphere, you can see the planet's magnetic field with these yellow lines here. This is for the Earth, of course. And the boundary of this three-dimensional cavity is the magnetopause, which is shown in pink. So this is the basic anatomy of a magnetosphere. I think most of you will be familiar with it. You'll notice that a lot of details missed off here, which is one of the reasons I chose this diagram. So what we're now going to talk about is a bit more about that interaction between the solar wind and our planet's magnetic field. So it's not in any way a static situation like we just showed. We needed to show that diagram in the last slide so we could introduce the anatomy of the magnetosphere. But in reality, everything is changing with time. Magnetospheres are extremely dynamic on various timescales. So the solar wind, and one thing I should have said on the previous slide is, and I'll actually skip back to make this point, the solar wind exerts a pressure on the Earth's magnetic field, which pushes back because the magnetic field doesn't want to be compressed, and it exerts an outward pressure. So that's what dictates the size of this magnetosphere. It dictates where the magnetopause is. So I'll jump forward again. So the solar wind interaction, as the solar wind varies, and it varies really dramatically on various timescales, it changes the pressure. And so the Earth's magnetic field isn't getting stronger and weaker on those, dramatically at all. And so the magnetopause of the Earth moves in and out. So that's the first way that the solar wind influences the magnetosphere itself. It appears it's excluded, but it can affect things. So the first way is, as I just said, making the system shrink, be compressed, and then expand. And that's always happening for the Earth as our sort of reference system. Also, there are ways in which the solar wind can get into the magnetosphere. So I'm not going to talk about the cusps where you can get direct entry. This is more processes that operate at the magnetopause that break down what you can think of as our planet's natural magnetic shield. So for the Earth, there are two main sort of modes of interaction that are talked about. And they're illustrated on this slide for a general magnetized planet, but it may as well be the Earth. It's roughly to scale. So the first, and this is a 3D cutaway, because of course this is a three-dimensional system. So the solar wind's coming in from the bottom left. So the first type of interaction is the classic one, which goes all the way back to Jim Dungy in the 60s, a seminal paper he wrote in 1961. And it involves magnetic reconnection, which many of you probably do research on. And so you can see there are lots of red field lines here. The one on the far left, which is connected to the solar wind at both ends, that's the sun's magnetic field and interplanetary magnetic field line. And then you'll see there's a field line that connects to the planet at both ends. So that's the so-called closed magnetic field line. And those two can come together. Magnetic reconnection can occur, which releases energy and accelerates particles. And you end up with these two highly kinked magnetic field lines, which then accelerate up over the poles. And now I don't have time to go into all of this, but of course, this is the driving part of the so-called Dungy cycle. We know it's the primary way you drive energy and create dynamics inside Earth's magnetosphere. You load magnetic flux into the tail. Eventually, you can get reconnection into the tail. So this is a way solar wind energy can get into the system, into our planet's magnetosphere. Now, there's another mechanism by which the solar wind can influence the Earth's magnetosphere. It also dates back to the 1960s in a seminal paper, or a couple of papers by Axford and Hines. And that's what they term the viscous-like interaction, which is illustrated in the bottom right of this diagram. Now, this is another hot topic in Earth magnetospheric work. Lots of people use data like, for example, from the MMS spacecraft to look at what's happening in vortices structures on the magnetopause caused by instability growth. So back in the 60s, the idea was that magnetohydrodynamic or fluid, describing the plasma as a fluid, you get all these wave modes and the waves bounce around. And the idea was when they bounce off the magnetopause, they can transfer momentum across it. And so even though there's no collisions, and even without reconnection, you'll still get transferred momentum, and that is capable of creating a long magnetic tail. Now we know that a particular instability called the Kelvin-Helmholtz instability is very important for this, because when it grows, it's a flow shear driven instability, little perturbation on the boundary, if the boundary is locally unstable, that perturbation will grow and it will propagate first as a wave, and then it will evolve and enter its nonlinear phase. And you can end up with this really rolled up structure you can see on the bottom right of this diagram. So these are the two. There's lots of other ideas and ways in which the solar wind energy can get into Earth's magnetosphere, but these are the two primary ones we look at. And the primary one is global magnetic reconnection. And luckily for the Earth, we can talk about things like voltages that are applied to the system, which is what you really want. It's your target if you're trying to understand drivers of magnetospheric dynamics. And for the Earth, global magnetic reconnection is at least a factor of about 5, like order 10, higher than the voltage applied by the viscous-like interaction. Key point is that they're both going on. One tends to dominate. There are some conditions where the viscous-like interaction is dominant because global magnetic reconnection sort of shuts down under, well, largely shuts down under Northwood IMF, for example. Okay, so I'm gonna, the risk of spending too much time on this slide, I'm gonna stop there. These are the two key ideas here, and it's coming from this reference system, Earth's magnetosphere. Now, to sort of conclude the introduction, and I think this is quite predictably the next stage for this line of thought we're going down. Different magnetized planets in the solar system are at different distances from the sun. The solar wind is different, its pressure is different, and the planet's level of magnetization is different. So this compares simply the scale of some of the planetary magnetospheres in the solar system. So the top right is the Earth, which is the diagram we saw a couple of slides ago, where we introduced the anatomy of a magnetosphere. There's a little bit more on here. And then you can see that if you put a rectangle around the Earth and then zoom in, you could fit Mercury's magnetosphere in there. So that's much closer to the sun, and the planet's less strongly magnetized. So you've got a higher solar wind pressure, weaker magnetic field to stand it off. And so you get a tiny magnetosphere, and Mercury occupies a much more significant volume of the magnetosphere than the Earth does in its system. But then if you go out to Saturn, more strongly magnetized planet, 10 times further away from the sun than the Earth, you can see, hopefully from these zoom-ins, that the Earth's magnetosphere would fit pretty much within the planet, or just around, a little bit bigger than the planet. So Saturn's magnetosphere is enormous, but it's got the same basic structure, solar wind interacting with planet's field. And finally, Jupiter's is the biggest coherent structure in the solar system, biggest magnetosphere, of course, and that's shown in the bottom left. So there's a lot of diversity. This is just talking about the scales, and there's a lot of other ways we can separate these magnetospheres out and talk about the differences between them. So the motivation behind this work I'm presenting in this seminar is what is the nature of the solar wind interaction with different magnetized planets? So the Earth, as I keep saying, that's our reference system, but we've got some observations now, growing numbers of observations made at these different planets like Mercury, Jupiter, Saturn. Hopefully one day we'll have more from Uranus and Neptune. And there are two questions here. So the first one that I'd like to address is, what's the nature of the interaction? And what I mean by that is, we've seen that at the Earth, the solar wind is important for driving energy flow, but we've also talked about how it's primarily through this idea of global magnetic reconnection happening globally across the magnetopause on the day side, and that there's this other competing, but generally not as important mode, which is this viscous-like interaction. And so we can't assume, especially since the solar wind conditions vary so dramatically with distance from the sun, we can't assume that every case is going to be Earth-like. We need to reopen the question of which of them is dominant. And that's question one, really. Does global magnetic reconnection dominate at all these other magnetospheres like it does at the Earth? Or is the viscous-like interaction instead dominant, or are they similar importance? And that leads on to this. The way to then answer that question, of course, is to look at the fundamental processes, the primary processes that underpin them. So global magnetic reconnection is primarily because of reconnection happening at the magnetopause, and the other is to do with instabilities like Kelvin-Helmholtz instability, rolling things up and providing the anomalous viscosity. Now, question number two, we're not going to touch on in this seminar, but it's really an important one as well. How important is the solar wind for driving energy flow inside all these different magnetospheres? The reason we're not going to touch on number two is because For that, you need to bring in knowledge of the interior of the magnetosphere and whether or not there's an active moon, for example, and at Jupiter and Saturn, that's very important. But what's necessary to answer question 2 is to also address question 1, and one of the elements is the solar wind driving. So I've said that we've got some interactions growing at planets that aren't the Earth, which are strongly magnetized, like Mercury, Jupiter, Saturn. However, those observations remain limited because they're single spacecraft observations. And unlike a lot of this spacecraft going around the Earth, these spacecraft rarely spin. Juno's the first spinning spacecraft, and Bepi Colombo's MMO spacecraft will be another spinner, but it hasn't arrived in orbit yet. So observations of the interaction directly at the magnetopause are limited compared to the Earth. So what I'm going to do now is I'm going to go into some of the basic theory about those 2 fundamental processes. So we're going to address question 1, and we're going to look at magnetic reconnection and Kelvin-Helmholtz instability and try to shed some light on what the answer to question 1 might be. Okay, so this is where I start throwing equations in, and I hope I maintain my audience through all of this. So this is some basic theory of those 2 key processes, and I hope a lot of this, and I expect a lot of this, will be familiar, which will be to my advantage. Now, let's just consider a boundary between 2 magnetized a boundary between 2 magnetized plasmas, like a planetary magnetopause, where you've got the solar wind, shocked solar wind plasma on one side, and the magnetospheric plasma and magnetic field on the other. So here we are, there's our boundary in orange, and above it, you've got the first magnetized space plasma, and below it, you've got the other one. And let's set up some conditions immediately adjacent to that boundary. You have magnetic fields either side, B, you've got bulk flows either side of the plasma, V, and plasma mass density is given by this rho. And you'll see that the subscript 1 I'm using for one side and subscript 2 for the other side. And we've set this up nice and simple. We've got anti-parallel fields, anti-parallel flows, and then of course the densities of scalars. Okay, so that's our setup here. So now let's think about magnetic reconnection happening at that boundary. Now, this first set of equations is the scariest one, but because it might not be as familiar to everyone, but I'm going to simplify it with assumptions to bring it back to the familiar in a moment. So this top equation is an equation for the reconnection rate, which is really the reconnection electric field strength. So if reconnection was to happen at that boundary and those magnetic field lines were to come together and be reconnected, then it would happen, there would be a certain rate at which you open up magnetic flux. In other words, you create reconnected flux, and it's closely tied to the rate at which you release energy from the field. And so I'm not going to go through all of these different terms, but you'll see some of them, you can already see what they are. You've got magnetic field on one side, magnetic field on the other side. There's this flow subscript O, which is the outflow speed, which you can see below. It's once again a term which involves magnetic fields on either side, density on either side, etc. So there's a paper, really nice theory paper, that comes up with all of this. Now, if we make things a bit simpler and bring things back to our sort of textbook understanding of reconnection, first of all, let's set the flow shear to 0. So you'll see in that equation at the top, there's this V1 minus V2 squared over V0 squared. So that term reflects the fact that if you've got a large flow shear between the bulk plasma flows, if that's really, really fast, then it's bad for reconnection, because if it's faster than the characteristic speed of reconnection, which is the Alfvén speed, then it's difficult for reconnection flows to be set up. So let's keep things simple and forget about that for the minute, and just say there's no flow shear, and then we can come up with this proportionality relationship, which I'm calling equation 1. So we're going to come back to this equation 1 later on. So this says that the reconnection rate is proportional to this term. So you'll see this is a function of only the magnetic field strengths on either side and the densities on either side. And so that's important. I'm trying to isolate here how reconnection rate from reconnection, of course, is influenced by changing the magnetic fields and the densities. And so this is where it becomes really familiar, I hope, if we now make conditions symmetric. So that's to say, if we let B1 equal B2, and we let ρ1 equal ρ2, then we end up with this relationship in the bottom right, where the reconnection rate is proportional to the symmetric magnetic field strength adjacent to the boundary times the Alfvén speed. Now, I think Alfvén speed might be a familiar concept, but just to repeat, it's the speed at which a wave would move along the magnetic field line. It's one of the MHD wave modes. The stronger the field, the faster those waves propagate, and the more plasma there is, the slower they propagate, because you're displacing the field line and there's a tension force trying to drag the plasma back. And the more plasma there is, the more difficult that is to do. So the Alfvén speed is really important. It's going to come up from now on multiple times, and it's the characteristic speed at which reconnection happens. So what you can see there is the higher the Alfvén speed, the better for reconnection, which makes sense, right? It happens faster, it releases energy quicker. And we're going to come back to that equation 1 later on. Okay, so now let's think about Kelvin-Helmholtz instability. So this is, as we said earlier, a flow shear driven instability, and we've got a flow shear here between these two bulk plasma flows, V1 and V2. So there's a very classic condition for the instability to grow. So this is different to what we looked at for reconnection. This is now a condition. You'll see that the left-hand side here has to be greater than the right-hand side at any point on the interface for the boundary to be locally unstable to this instability growth. And so K here is your wave vector for your perturbation, your mode that's growing. You've got a flow shear, and so the right-hand side has got densities and field strength. So you can maybe guess what we're going to do. We're going to try to isolate how changes in the field strength and density affect this beast compared to reconnection. So the first thing we can do to make things simple is, let's say that K is parallel to the flow shear, which tends to be a good assumption because that maximizes the left-hand side, and that's the direction you tend to grow perturbations in wherever there's a flow shear. So then let's now only think about the right-hand side, and let's call it capital I. So it's really a stabilization term, because the bigger it is, the bigger that right-hand side is, the more likely the boundary is going to be stable. And once again, we can make it a proportionality relationship, which I'm calling equation 2. And so this is how the ability of the boundary to remain stable depends on densities and field strengths. So let's just talk for a second why that is. If your fields are really, really strong, either side, you'll see that this I parameter becomes bigger. And that's because the magnetic fields exert a tension force. They don't want to be twisted around. You've seen that this instability twists everything around and makes these vortices structures. The field tension can stop that. It makes it more difficult. And so magnetic tension forces are captured in here. And also the densities. So it's a different relationship with density. You want similar densities either side for this instability to work. You don't want a big asymmetry, and you don't want them both dropping down to very, very, very low values, because then the I parameter blows up. So similar to what we did for reconnection, there's a relationship involving field strengths and densities, and it's a proportional relationship, which I've called equation 2. Now, once again, we can make things symmetric. So set the field strengths equal, and the flows and everything, and the densities. And what you then get is this I parameter is proportional to the Alfvén speed squared. So just to summarize what we've just done, which is this is the point I'd hope that everybody follows me up to, because this is the key point really of the whole seminar. So what we've seen is, for reconnection, as a general rule, lower Alfvén speeds are bad for reconnection, to put it very crudely. And the opposite is true. Higher Alfvén speeds are good for reconnection. That's because lower Alfvén speeds mean weaker reconnection electric fields, lower reconnection rates. Now, the opposite is true of Kelvin-Helmholtz instability. So if you have a lower Alfvén speed, that's actually good for Kelvin-Helmholtz instability growth, because we've seen that the stabilization term is proportional to VA squared. So if it gets lower, then the stabilization term gets lower and the boundary is more unstable. So you can think of that as a diminished ability for magnetic tension to stabilize the boundary. So straight away we can see the Alfvén speed is very important. It acts in opposite directions for these two things. So if it's going higher or lower, it's causing a divergence of these two processes. It affects the two of them in opposite ways. So that leads to this question. what does all of this mean for the solar wind interaction with different magnetized planets? And the key thing here is, how are the magnetopause conditions going to be different? So we know that the solar wind conditions, this is upstream of the planetary bow shocks, we know that those conditions are very, very different because these planets are at very, very diverse distances from the sun, so-called heliocentric distance. So this plot just shows classic scaling laws that have been defined for the solar wind and how its bulk properties, sort of typical properties, so ignoring lots of variability. So typically how things like the solar wind density change as the solar wind flows to greater and greater distances from the sun. So in both of these panels, A and B, you'll see the x-axis at the bottom is heliocentric distance. So going from close to the sun, and you'll see this first vertical dashed gray line is Mercury's orbit. Then at 1, of course, that's the Earth, because we're working in units of AU. Jupiter's at 5, then you've got Saturn at 10, Uranus at 19, and Neptune all the way out at about 30. So this encompasses all of the strongly magnetized planets in the solar system. Now, panel A shows the sort of classic solar wind parameters. The speed, it's the most boring one in here. The acceleration happens closer to the sun, and you can effectively assume it's very, very similar speed solar wind at all of these bodies, at all these different distances. Now, the plasma density, this is the log-log scale, so this is the slope of -2. So it's dropping as 1 over r squared, which makes sense for spherical expansion of the solar wind. And then the magnetic field has a slightly different scaling law, but it's still a drop off with distance, as you'd expect, because that's the interplanetary magnetic field created by the sun. The further you go away, the weaker it gets. Now you can put these together and you can look at this important parameter we've identified, the Alfvén speed. So in panel B, the sort of light blue with the left hand y-axis, that's the Alfvén speed in the solar wind. And we've seen that's a key parameter, as I just said. It's higher closer to the sun, and it drops as you go out from the Earth. It continues to drop, and then it plateaus where the giant planets sit. And so this is really important. You also plotted here as the Alfvén Mach number, which is how much faster the solar wind flow is than the Alfvén speed. And so you get a similar kind of thing, but flipped for that. It increases, and then you get higher Alfvén Mach numbers at the giant planets. So we can straight away see that things are likely to be different with these different magnetospheres, particularly when you get far out. Okay, so at this point, I won't have time to go through all of the detail here, and I think it might be a bit too much. So if anybody is interested to see the nuts and bolts, please see the paper. I'll put the reference up again on the summary slide. So what I do in the paper, and I'm going to show you the punchline of here, is I derive what I'm calling solar wind driving proxies. So I'll just summarize this block of text here. The key thing is, let's imagine we've got a toy magnetized planet, and we can put it any distance from the sun we want. And now let's consider the subsolar point on its planetary magnetopause, which is of course the shortest distance between the planet and the magnetopause, approximately along the planet-sun line. That's the subsolar point. And now let's neglect the plasma pressure in the magnetosphere, so that the internal pressure is pretty much the planet's magnetic field pressure. So this is the sort of thing you would do in early on in learning about space physics, to work out the Earth's magnetopause standoff distance, Right, so that's that situation we're considering. Now we can do a lot of different things. Apologies if this is a little bit overwhelming, because I don't have time to go through each one separately. We can introduce, first of all, the scaling laws we just plotted for the upstream solar wind. And that introduces a couple of constants, because we need to normalize to what the conditions are like at the Earth. We can then also introduce some description of how those upstream parameters relate to the conditions in the solar wind just outside the subsolar point on the magnetopause. And so they're obviously going to be higher. The field strength of the solar wind is going to be higher, density is going to be higher. And so you introduce more constants now, which are really free parameters. What you can then do is, whatever distance from the sun you're considering, and whatever distance from the sun you put your toy magnetized planet, you can now balance the pressure to get the magnetic field strength in the magnetosphere just inside the subsolar magnetopause, which leads to another constant you're about to see in some pretty scary equations, which is what I'm calling derived constant, capital A. Then you can pick a plasma mass density in the outer magnetosphere. It corresponds to negligible total plasma pressure, but you still need to pick a density, and that's this constant rho subscript m. And then finally, equation 1 and 2 a few slides ago. Those are proportional relationships for each of the two fundamental processes, and they show how those processes depend on field strength and density. So I'm calling them field strength density proportional relationships. And that leads to two proxies. So at this point, we should probably brace ourselves. So these two equations, there's a lot going on, but they're really simple to derive. And as I said before, please see the paper if you want to have a look at it and check that I've got it right. So these are the two proxies. So I just want to say where they come from. So the one that's shaded pink, that's for reconnection. It's a proxy for global magnetic reconnection at the planetary magnetopause and how important it is. And it comes from the reconnection rate, of course, because that's what we were looking at in our basic theory of reconnection. We were focusing on the electric field strength. So I'm now calling that capital D, subscript R. And to get this, you take equation 1 and you re-express it with all of those things listed in the bullet points above. So there's lots of constants in here. And the one term I haven't mentioned is capital R. Capital R is distance from the sun, heliocentric distance. So what we've now got is an equation which is a function of just R. We pick values for our constants, and they are free parameters, so we have to consider the sensitivity to what we choose for those within reasonable limits. But capital R is the key thing. We can now talk about how that parameter changes with distance from the sun, and that's what we really want. Then this blue shaded equation is for Kelvin-Helmholtz instability, but this is coming from that stabilization term, which we focused on a few slides ago for that process. And once again, slightly simpler equation, you've got these constants and capital R. So this is also a function of distance from the sun. And remember, this is a proxy for Kelvin-Helmholtz instability growth at the boundary, and it's a stabilization term. Okay, good. So this slide now, this figure shown in this slide is the sort of second punchline of the whole thing. So we've already talked about how the alphane speed is a key parameter and it affects the two processes in an anti-correlated way. But this is now extending that. We've got those proxies we just derived. We can normalize them to their values at Earth orbit. So this theory we're doing at the minute, what we're going through, it doesn't tell you absolute numbers. It's only for comparison between the processes. And in a minute, we'll talk about the implications of that and how it limits the conclusions we can draw. So at the Earth, you can take those two parameters we just showed equations for, and we can normalize them. So we get unity at the Earth. On the left-hand side, sorry, the x-axis is once again heliocentric distance, or capital R. The left-hand scale is for that reconnection proxy, and the right-hand scale is for the Kelvin-Helmholtz instability proxy. So we normalize them to Earth, and that's not to suggest that they're of the same importance of the Earth. We know they're not. We know that global magnetic reconnection is, quite a lot more important depending on the solar wind conditions for driving energy through Earth's magnetosphere than a viscous-like interaction underpinned by Kelvin-Helmholtz instability. We know that. This is just to show how the situation will vary at other planets. When you move away from the Earth, you go towards the sun and Mercury, you go away to the giant planets. It doesn't tell you if the balance of power completely shifts so that the other dominates or whatever happens. It just tells you which way things are going to move. So just to sort of expand on that, let's look at Mercury. So Mercury, closer to the sun, we know that the alphane speed of the solar wind there's higher, for example, so you can sort of guess what's coming. And those of you familiar with Mercury's magnetosphere won't be surprised to hear this. But this theory is consistent with a very strongly solar wind driven system by magnetic reconnection primarily. So compared to the Earth, what this plot is showing is that at Mercury, it's even more, global magnetic reconnection is even more dominant over a viscous-like interaction for driving the system. And it's because the solar wind conditions are different. And it would be very surprising in a way if it was Earth-like at every magnetosphere, because we've already talked about how the solar wind changes so much. So that's the first sort of point about Mercury. Mercury is really like the Earth, but with an even more dominant global magnetic reconnection type interaction. If you go away from the sun, you can see the opposite happens. Magnetic reconnection as the primary driver of energy flow through the system drops away. Your reconnection rates drop lower and lower and lower. And we've known this for a long time. And you see it in observations made at those boundaries. The viscous-like interaction underpinned by Kelvin-Helmholtz instability starts to look more favorable as you go away, because your ability of the boundary to remain stable is getting less and less and less. You'll notice that the scale on the far right, the y-axis, I've flipped it because a lower value of this stabilization term is positive for Kelvin-Helmholtz instability growth. So I needed to flip it so that we're comparing like with like, so to speak. So what we can say from this plot, and I think it's robust, you'll see that there's this range here. I haven't mentioned where that comes from. That range comes from choosing those three parameters to be anything you want that makes physical sense. So as long as your solar wind is compressed across the bow shock, you'll get this kind of thing. And the only way you deviate from it if you introduce things that are unphysical. So there's a very wide range here, and you still get this variation, this monotonic change. So now we're pretty much at the end of the seminar, but what does all of that simple theory applied mean? So go back to this diagram which shows pretty much the Earth with the two types of interaction. So what it means is when you go towards Mercury, as with what he said, the dominant interaction becomes even more so global magnetic reconnection. But what it means for the giant planets is more interesting. It means that the viscous-like interaction, very likely, I think it's a robust conclusion that it's more of greater relative importance when you go further away from the sun. We've seen why that is. Stabilization of the boundary becomes less effective, reconnection rates drop, and at all the giant planets, the viscous-like interaction is of greater relative importance. Now, it's important to note, we can't say, based on what we're talking about in this seminar alone, we can't say that a viscous-like interaction becomes dominant. Some of my colleagues think that's the case, and they have evidence they present, and they may well be right, but based on what we're talking about here, we're showing that it's very likely, it's plausible, and I think it's robust, that the viscous-like interaction becomes more of a player compared to global magnetic reconnection at the giant planets. And it leaves open the possibility that it becomes dominant and that the type of interaction is flipped at the giant planets compared to the Earth. And that maybe those magnetospheres and the interaction at their magnetopauses is a much more messy type of interaction, like what's illustrated in the bottom right of this diagram. Okay, so now this is just my summary slide. So I've already said what's in these bullet points, and of course the reference is given at the bottom there. At the very end, I just want to, in closing, mention a couple of things which might head off a few questions that are coming my way. Things we haven't talked about that are important, that people may quite rightly have picked up on. One is the variability of the solar wind. So we've only looked at, in this theory we've just gone through, we've only looked at the typical conditions in the solar wind. We haven't thought about variability, and in particular variability of those typical conditions really over the solar cycle. And this is a point that's been made by some of my colleagues in a paper after the one I'm talking about here was published. And it's true, when you if you focus on the solar wind is extremely variable, and so all of this is going to be subject to a lot of variation, just like at the Earth, where sometimes a viscous-like interaction becomes the main way the solar wind's influencing the system. When you consider the solar cycle, the state of the heliosphere is very different at solar maximum compared to solar minimum. And you know, some of my colleagues at Goddard have pointed out with lots of data taken throughout the heliosphere that the Alfvén speed in the solar wind is higher in the outer heliosphere at solar maximum. And so that is going to affect this balance of power. What it doesn't affect is the variation from the Earth to the giant planets. So whatever the state of the heliosphere, it produces the situation at the Earth, and at the outer planets, you'll have a more important viscous-like interaction. And we still don't know whether the viscous-like interaction becomes dominant. So that remains an open question, but there's very likely to be a very strong dependence on the solar cycle. So that's all part of this, you know, further questions to be addressed here. The other thing to say is we've used a sort of toy magnetosphere to make our points here. And we've neglected internal plasma pressure, which is a bad assumption for Jupiter and Saturn. But at Jupiter and Saturn, that if you relax that and you try and include plasma pressure inside the magnetosphere, it only makes the argument stronger because it further decreases the alpha vane speed in the outer magnetosphere. If you put plasma in there, you inflate the magnetosphere, you push the field strength down in the outer magnetosphere, then Jupiter and Saturn are probably the prime candidates for places where the solar wind interaction is primarily viscous-like. Now, Uranus and Neptune are really mysterious and we don't really know. The solar wind is probably the main driver there in the absence of evidence for strongly active moon like Io at Jupiter and Enceladus at Saturn. So we haven't seen mass-loaded systems with Voyager 2 at either of those ice giants. Solar wind may be the most important way to drive energy. One key thing here is how much plasma mass density is in the outer magnetosphere. If it's Earth-like, that's an assumption that I've made in all of this theory, and the argument holds. You would need a lot of plasma mass density there, though, to make this conclusion not apply to those two ice giants. And Voyager 2 didn't see very high densities just inside the magnetopauses. So those are just some things I wanted to mention. So I think the basic idea here is robust, but it is limited. So I think it's still a very open question and something that motivates future exploration and research to try to understand exactly what the solar wind interaction is like as a big picture, especially at these giant planets where it may be totally different to the interaction at the Earth. Okay, I'll stop there. Thank you very much for listening. Happy to take questions.
Oh, thank you very much, Adam. I think it was a very great seminar. Actually, I really enjoyed very much and I learned something today. So that's, yeah, thanks so much for this nice overview of this solar wind interaction with the magnetized planets. And we have already a couple of questions in the chat, but I think maybe people can actually open the microphone and then ask the questions. So the first one is by Katrina Jackman. Do you want to?
Yeah, I'm here. Can you hear me?
Yes.
Hey, Adam, how are you?
Hi, Katrina. I'm good.
That wasn't my question, by the way.
Oh, I thought I got off easy for a minute there.
That's it. Yeah, great talk. So I just wonder if you can expand a bit about the expected nature of Kelvin-Helmholtz of the giant planets, particularly in terms of local time asymmetries and what you might expect to see at dawn versus dusk and what you actually see at dawn versus dusk. Yeah.
So that's, we have observations at Jupiter's magnetopause and Saturn's magnetopause that start to build the picture. And you're quite right. There's a strong local time asymmetry. That's introduced at those systems because they're dominated by co-rotation. So the plasma inside the magnetosphere is going around with the planet in a qualitative sense. And so you introduce this asymmetry in the flow shear across the magnetopause. So that's really detailed beyond the very simple stuff I've been talking about in the seminar. And it produces the big dawn dusk asymmetry. And it also allows me to make the point that the boundary becomes unstable in some region. This is what we see at the Earth as well. And a perturbation in that region grows and it evolves, but it also propagates away. So what we've seen at the giant planets, which are unlike the Earth in this co-rotation dominated situation, we've seen that perturbations are often seen way away from where the boundary is unstable. So they grow where it's unstable and they move away. And so at first we were surprised about the asymmetry we saw at Saturn, which was the opposite of where the boundary is unstable. But simulations since have shown that it's because of that propagation effect.
Cool, thanks.
Thank you.
So there is another question by Edmund Henley. So maybe you can.
Sure. Thanks, Adam. Just a really naive question. Can you look at this in an alternative, more geometrical interpretation? So you've done this of a theoretical one, concentrating on the subsolar point. Can one look at determine kind of characteristic spatial scales for reconnection versus, say, the Kelvin-Helmholtz structures, and look at the relative area of the magnetopause that's available at each planet for the different processes, which presumably might change because of, say the different flaring or the relative size of the magnetopause at each planet versus a characteristic scale of the process for this to operate over? Or does this is this the same as, does this give the same sort of approach as yours? Does it not work because these things are scale free, or yeah?
Yeah, that's a very good question. That's why I think that the conclusion drawn here is qualitative. So I guess, correct me if I'm wrong, Ed, but another way to state your question is the bigger the magnetosphere, the better for both processes, because you get longer X lines, meaning higher reconnection voltages, and you get larger regions of instability where things can grow. And we don't know how, we have a good idea for the former. If you've got a bigger system, a bigger X line, and so you can say you've got a reconnection electric field, you multiply it by how long your X line can be. And people have done that to come up with reconnection voltages, including myself. For Kelvin-Helmholtz instability, we don't have the same kind of framework. So bigger systems are going to be better because the perturbations can grow for longer in these large regions of instability as you scale everything up. But it's not clear if it scales in the same way. And this is why we can't go I don't think at the minute we have the theory to go beyond what I've just talked about and say quantitatively which one is dominant over the other. Another way of putting that is if Kelvin-Helmholtz instability is scaling differently with the size of the system to reconnection, then it might mean that although conditions become more favorable for a viscous-like interaction, it's also possible that global magnetic reconnection remains dominant because the bigger scales favor that process more. In other words, there's another parameter in here which we haven't got a handle on. And as I said, it's why I think we can only be qualitative about these things we can get a handle on. Hopefully that answers your question.
Yep, brilliant, thank you.
Cool, so there is another question by Jack Ray. So maybe you want to say?
Good morning, thank you for the seminar. I just wondered if the viscous-like interaction were dominant at the outer planets, what would be the most obvious observational signatures of that?
So the first would be, it's another good question. It's tricky to separate these from the observations we've got. So, you know, if we could throw a load of spacecraft around Jupiter, we'd figure everything out, I'm sure, if we instrumented them properly and put them in the right place. With the observations we've got, it's very hard to separate these two things out. One the things you would want though is observations at the boundary, because the signatures of a global magnetic reconnection happening is different to these big vortex structures that are forming. And I should also say that one process tends to drive the other, but we're focused on the primary process. So whenever you get a viscous-like interaction, you do get reconnection happening inside the vortices, but it's not global, it's local and it's intermittent, opening and closing, people think. So the first thing would be a disturbed boundary, very disturbed boundary. The other thing, which Katrina was talking about, is a dawn-dusk asymmetry, which you could explain through a flow shear and then propagation of the perturbations. That's something which would point of one over the other. Another is, the tricky one is open flux in the system. So if you were over the polar region, and if you could work out, which we can't, from a single spacecraft or from existing data sets, whether a magnetic field line is open or closed. We can say if it's closed, but it's very hard to say if it's open or not with the observations. That's another way of doing it. And even then, in that situation, I've already mentioned the viscous-like interaction can produce open flux because of this reconnection happening locally inside the vortices. So yeah, that's a tricky question to answer. And I think the boundary and seeing the perturbations on the boundary and asymmetries in the boundary is going to be key. And I should note that at Saturn, where we've got the most magnetopause crossings of all the giant planets, it's a real mess at the boundary a lot of the time. And there's been a lot of work done looking at the perturbations. So it seems consistent with viscous-like interaction being more important. Whether or not it's dominant, I think a lot more work is going to be needed.
I see. Thank you very much.
Thanks.
Oh, so is there any other questions? So you can just raise your hand or write in the chat. And well, meanwhile, I have also a question. So yeah, so you just focus on magnetized planets, but I mean, I work mainly with Mars, and even if it's considered a magnetized planet, so I still have strong crustal magnetic fields that actually interact a lot with the solar wind. And actually recently, since Maven arrived to Mars, so we have seen that there are much more dynamics that we originally thought. So I don't know if you have considered as well, I don't know, to include in your study a kind of hybrid planet as Mars.
Yeah, absolutely. I think that the scaling with heliocentric distance that I showed, that works for if you were to put Mars in there, and you were to think, as you say, about the more localized regions that are shielded of the planet because of remnant crustal magnetization, which I think is the explanation for that. Yes, the same sort of thing applies. So you would get a different proxy for reconnection through this reconnection rate, and you would get a different propensity for Kelvin-Helmholtz instability. I think Ed's question about scales comes in there, and we'd have to think about how big a region and how long is needed for a perturbation to grow, what sort of flow shears you might get. Reconnection can happen a lot more quickly.
Yes, it will also vary because the fields rotate with the planets. So I guess it will be also, like a diurnal variation or something like that.
It's true. And that diurnal variation is other planets where that's going to be really important are Uranus and Neptune, which are really a real mystery. And that rotation is going to change everything. So yes, it's true. And this can certainly be applied to looking at other planets, even if they're not strongly magnetized like Venus. These processes happen around the planet. So as long as we're careful about what's happening to the conditions, the solar wind, which is the focus here and how it scales, is still applies wherever they are.
Cool. So there is another question by Simon Opie, so maybe you can ask.
Yeah, sure. I was just wondering whether there's another sort of layer of complication due to the interaction between the two modes. And the thing I was thinking of in particular is the reconnection exhausts would presumably feed into the conditions for Kelvin-Helmholtz KH instability, for example. So whether you can effectively separate the two out as kind of conclusively as that initial treatment suggests.
Yeah, that's a good question, and I don't think it will be easy to separate them. And you may well be right. I think it may be extremely difficult to separate them, as you point out. So I mentioned viscous-like interaction and growth of the Kelvin-Helmholtz instability leading to localized reconnection. So your primary process there is Kelvin-Helmholtz instability. But as you say, the same is true for the other process. If you have big reconnection X lines, they affect the flow. You can get Kelvin-Helmholtz instability growing at the edge of the exhaust, actually. In some simulations, they see that. And the exhausts themselves change the flow pattern, as you say, and affect where the boundary is unstable versus stable. So yes, I don't have a good answer to that question. And I think it's probably going to be very tricky to separate them. It's true.
Thanks.
Cool. So is there any other questions? Okay, so I don't see any raised hand. Let me check it. No, I don't see anyone and no more questions. So I guess we can finish here. So I just wanted to thank you again, Adam, for this very great seminar and for accepting the invitation for being here today with us. And also to thank you to everyone that has been, we have been near 50 people today. So that's really, really great. So thank you so much for being here. And our next seminar will be at the beginning of January, and we still need to find a speaker. So we will send we will send an email with the details later. But for now, I just want to wish you Merry Christmas to everyone in here and have a good holidays. And I'm sure this is also on behalf of everyone in the MIST Council. So thank you so much, and really hope to see you everyone later in January. Cool.
Thanks everyone. Thanks for having me.